talked about kinetic energy of the reactants, we have a different kind of graph than we had before. So yesterday's graph, or the previous day's graph, was similar. It had PE here. We talked about potential energy, and we talked about how the energy of the reactants is different than the energy of the products. So what we're talking about here is slightly different. We're talking about the number of molecules on the y-axis and the kinetic energy on the x-axis. So I'm specifically pointing this out to you because it's notably different than the previous graph. So let's think about this graph differently than the ones before. So before we had a hump and it was activation energy. That's not what this is. In this graph, the energy is increasing. So at each different point along the x-axis, there's more energy. Okay? Energy on the x-axis. So totally different graph, essentially. And we're talking about a distribution curve. So some of you have been asking me this year about curving grades. The idea of curving grades is based on this idea of a bell curve. This is almost a bell curve, although it's not. You'll actually notice that it's kind of shortened on this end, and then it's like elongated on this end. So this is a hill. If this was a ski hill, this would be a much higher challenging run than this hill. Okay? I know you guys got skiing on your brains or snowboarding. So this one is a steeper curve here. It goes up and then it kind of tails down on this end. What we're talking about is the kinetic energy, aka essentially the temperature. So when you guys have a sample of anything, let's say it's this water in this bottle, this sample has a variety of kinetic energy. All of the molecules are actually not at the exact same energy level. There's what we call a distribution curve. So just like all the people in this room, some people are very awake. They're just raring to go. I don't know who that person is. It is not me. But they are like excited to do something at the end of the day when the bell rings and they have some energy in them, pep in their step. And other people did not get enough sleep, too much siege all night, whatever. And they're like dragging, hardly awake. And then there's the majority of people who are just at an average kind of amount of energy. So I want you to think about that, actually a very good analogy for any sample of molecules. So in my sample, we're talking about our reactant because we're trying to see if our reactants have enough energy to react. So in our reactant sample, there's some lazy siege players that just didn't have any energy. They didn't get any sleep, okay? The average kinetic energy is somewhere in here. So this would be what we call temperature, the average kinetic energy of the sample. And then some of them just happen to have a lot of energy. They're extra, whoever's the extra, okay? So we have a distribution. And so when we talk about kinetic energy changes, we're talking about what we can do to essentially squish or push this graph along these axes. So what we just wrote down, which I'll zoom out for people to write, if you're in the video you can just pause, is that the average kinetic energy is if it's higher. So that means if the average is further along this graph, so higher, more energy, then we'll have more reactants that have enough energy to react. So what I jumped over in the first graph is this line. They impose this line that says right here, if this was the amount of kinetic energy we needed to have an activation, then all of these particles are past the line and only these ones are before the line. So these ones don't have enough and all of these ones do have enough energy. So if we were to impose the bar here, if we were to say now we need to have, this is our minimum kinetic energy required to react, aka activation energy, right? So this is activation energy, essentially the minimum energy required to react. We have most of our molecules do not meet that threshold. What happens if we heat up this sole sample? So think of this, this is one case where you could actually picture this as molecules filling this all up, okay? So we have all of these molecules here that don't have enough energy. what happens if we heat up this whole entire sample? The graph will shift, and shift is a great word. We're going to talk about shift a lot. So all of these molecules, they're not all going to have the same, but they're all going to get more. So they're all going to shift this way. And if this line stays the same, we'll eventually have enough. So that's what the next page is talking about. So the next page is talking about increasing the temperature. When we increase the temperature, we don't just slide it along the graph. It's more like taking my finger and poking it. So it gets wider and broader. So it lowers that peak and it pushes out the distribution. You're not going to be asked to draw these distributions. It's just helping to explain to you why is it that with a higher temperature, we're going to have more reaction. Because more of the molecules are going to be past the line. So here's our activation energy line. And I'm going to zoom out a little bit so that you can see this. There we go. This is the line that we've imposed for activation energy for this particular reaction. The pink was the curve at 25 degrees. So as this line falls down here, following my eraser, this is how many molecules had enough energy at 25 degrees. At 35 degrees, so a 10-degree increase, the curve becomes flattened, so the distribution is spread out more. The distribution still starts at roughly the same place with some molecules with very little energy, but we have more molecules with more energy, this green section here, which is enough to start a reaction. Now, if this reaction was, say, for example, exothermic, it would start to create its own energy. And then the reaction could kind of like cascade. Does that make sense? There's going to be a lot of factors. We're looking at them one at a time. But once the reaction starts going, we've met our minimum kinetic energy required. We have enough molecules over the line. The reaction will take place. So then we can say, as a general rule, and it depends on other factors, that if we have a 10-degree increase, the reaction rate will double. This is only true if it's already slow. So you probably saw in your lab that all of your graphs are curves. They're not lines that are straight. The distribution will reach an asymptote or a kind of a maximum rate, right? It's obviously never going to touch 0 time. The reaction has to take some time. So it will level off at some point. There is a asymptote or a limit that can be reached. Okay, so the limit of how fast a reaction can happen is going to happen, and then the doubling of the temperature or doubling of the concentration will not double the rate anymore. But if it's already a slow reaction, a general rule is you can double the rate by increasing 10 degrees temperature.